We have three laws of thermodynamics. The first one is the one that is related to conservation of energy. Energy can be transferred, energy can be transformed, but energy cannot be destroyed or created out of nothing. The second law of thermodynamics is the one that relates a process to randomness. So for any spontaneous process, the entropy, which is a new thermodynamic property of the universe, increases. So let's go over the definitions. Spontaneous means that process, that specific process, it's happening without outside intervention. So it's happening by itself. And then entropy, which is our new thermodynamic property, it's an amount of energy similar to what we have for enthalpy. But this amount of energy is an amount of energy that is being released or formed when something is becoming disorganized. Okay? When particles are arranged randomly, now we have an amount of energy that is associated with that randomness, and that is the entropy. It's another state function, so we also look at the change in entropy. The third law of thermodynamics is related to this randomness. This one is relating the temperature and the randomness. So the entropy of a system will be constant, or it will remain constant when we have a temperature of 0 kelvins, which is the absolute zero. When you have 0 kelvins, that's the same as having negative 273.15 degrees Celsius. So when I'm going over entropy, I like to use my simple sketch to represent this movement of energy when something is becoming disorganized. So the sketch on the left, I have four circles, and let's assume that each circle represents a particle. So I have four particles on the left, and as you can see, they're very close to each other, right? They are arranged close to each other, and they are in a fixed position. My red arrows pointing in the direction of my particles towards. That represents an amount of energy. So with my red arrows, what I want to represent, it's an amount of energy that is required to have those particles organized. Now, moving to the right side of that sketch, I have four particles, right? But now they're not close to each other, they are in random locations. And I still have my red arrows, but now my red arrows are pointing from my inside of my sketch going towards the outside. So what I'm trying to represent with those arrows is a displacement of energy. The energy that was being used to have your particles organized is now an amount of energy that is going somewhere else. Okay? So when the particles are becoming disorganized, that amount of energy that is required to have things organized can actually be used to do something else. So your particles are more randomly arranged on the right side of my sketch. I'm moving from something very well organized to something that is randomly organized. So what is happening is that the entropy is increasing. You're going from something that is organized to something that is randomly organized, and the entropy of that system will be increasing. So since entropy, change in entropy, it's a change, right? This is always final minus initial. Whenever the entropy of a final state is higher than what you have for an initial state, your change in entropy is going to be a positive value. So when things are becoming disorganized, that change in entropy will always be positive. Okay? Now, the tendency of being disorganized, it's something that happens spontaneously. Okay? If the system or the process that is happening is becoming more organized, now the final amount of entropy is smaller than the initial, and that change in entropy will be a negative number. So we're going to be looking at changes in physical state, and we're going over the physical states that I have listed here: solid to liquid to gas. You know that particles in solids are very well organized. Okay? They're close to each other. They cannot move around because there's no space between them for those particles to be moving around. So solids are very well organized. Then we move to the next one, which is a liquid. So in your liquids, the particles, they can flow. Okay? There's space between your particles. So your particles can actually move to occupy new positions. And then finally we have gases, where you have a huge amount or a large volume between particles. In your particles in a gas, they feel no attraction for each other, which means that they can move freely. So we're going from things that are very well organized in your solids to things that are not organized at all in your gases. For liquids, we do have some sort of organization, less than a solid, more than in gases, because the particles in a liquid, they do feel attraction for each other. So when the physical changes are happening, moving from left to right, from solid to gas, okay, the entropy is increasing because your state is becoming more disorganized. Okay. So the higher the disorganization you have, the more randomness, the bigger that entropy value. Okay? So delta S, the change will be positive because your final entropy will be larger than the initial. Okay? If we're looking at that orange arrow moving towards the right side, the opposite direction, when you go from something in a gas state, very disorganized, moving towards your solids, which are more organized, now the entropy is decreasing. Remember, the more organized something is, the lower the entropy. So your final entropy now is going to be smaller than the initial. And if you calculate a change in entropy, you will get a negative number. So I have an example listed there, potassium chloride, and that's a solid. And this is an example for a physical change. You have your solid, and what's happening here is that the solid is being dissolved in water. So this is preparation of a solution. So you have your solid, and now on the right side, what you have is the ions. So you get the ions when your solid dissolved in the water. Now you have ions, which are represented by the AQ for aqueous. So your solid is more organized than what we have on the right side, because on the right side we have your solution. So this is an aqueous solution where the ions are dissolved in water, and you're starting with a solid. So you're going from something that is organized, your solid, to something that is less organized, which is your aqueous solution. So the randomness is increasing because you're going from solid to something aqueous. The final value for S will be higher than what you have for the solid, and this here represents something with a change in entropy that has a positive sign. Okay? Becoming more disorganized will always have a positive sign. So I have several examples here. There are three of them for you to determine if you have a delta S that will be a positive or a negative number. So you should pause the video and try to come up with your own answers and then compare your answers with the ones that I'm going to give you. So the first one, you have a liquid, methanol as a liquid, and that one is going towards a solid. So liquid moving towards a solid, that's becoming more organized. And your delta S will have a sign that it's a negative. Now on the second one, if you check, all that you have there are gases. So you cannot answer this question with the information that you have. There's something else that we need to actually answer that question. So all of the physical states are gases. So we need to focus on another thing in that reaction. So you see on the reactant side, you have 1 mole of nitrogen gas, 3 moles of hydrogen gas, and then on the product side, you have 2 moles of ammonia gas, NH3. So I'm going to underline my coefficients. On the reactant side, I have a total of 4 moles of gas. On the product side, I have a total of 2 moles of gas. So in which side do you think you're going to have more disorganization? Where you have a larger number of moles of gas, or where you have a smaller amount of gas? That's what we need to focus on to answer this question. So we cannot answer this question based on a difference in physical state because we don't have different physical states. All of them are given in gases, but we can focus our attention on the amount. The larger the amount of something, whatever it is, the higher or more likely that a bigger amount will be represented by more randomness. It's easier to organize 7 books than to organize 200 books. That's something that you can think about. So if I have 4 moles of gas, 4 moles of gas will be arranged more randomly than just 2 moles of gas. So this reaction here, it's actually going from something that it's more random to something that it's less random because you have only 2 moles of gas. So the delta S for that one, it's also negative. So now for the last one, you need to focus your attention again in the amount that you have, not just the physical states. So I'm going to underline my number of moles because all of the states are gases. So on the reactant side, I have a total of 2 moles. And then on the product side, I have a total of 4 moles of gas. So you're going from 2 moles to a total of 4 moles of gas. So this last one, the entropy, it's actually increasing because you have more chances of being your gas on the reactant side, the gases with just 2 moles are more organized than when you have 4 moles of gas on the product side. So for this one, the randomness is actually increasing. It's the only one out of the three that is becoming more random, or that the entropy is increasing as you move from the reactant towards the product side. So what you have at the end of this page is something for you to think about. It's something that you can think about, and you can relate this entropy or randomness with the enthalpy, which is something that we learned before. Amount of heat absorbed or released, that's related to the enthalpy. Now the randomness, it's related to the entropy. So try to think about what's happening when this ice cube starts melting. What's happening based on the randomness and the enthalpy. Now, when we combine the randomness of a process and the enthalpy, which is that amount of heat that is being absorbed or released, okay, we have now this new thermodynamic property, which is the Gibbs free energy. So for Gibbs free energy, we use the letter G. And since it is a state function, we're focusing on that change in the Gibbs free energy. So we have a mathematical equation that puts together all of these thermodynamic properties: the Gibbs free energy, the enthalpy, and the entropy. So the Gibbs free energy will be a numerical value, okay? So it's an amount of energy in joules or kilojoules. That numerical value can have a positive or a negative sign, in the same way that we have for enthalpy and entropy. Now, when we have a negative sign for a delta G, that represents a spontaneous process. And that number with a negative sign is representing the amount of heat that was not used, that was not absorbed, right, by that process, or it was not used to organize anything in that specific process. So when we have a negative number, that represents a net amount of energy that is being released by that process. Now, there are two things happening. Amount of energy or amount of heat can be required to organize things. Amount of energy or heat can be absorbed for a process to actually happen. So the enthalpy and the entropy are going to play a role on this final amount of energy that we're getting or not getting. So I have my equation here, and this is the easier way for you to think about the signs is to actually look at numbers. How adding or subtracting positive and negative numbers are going to give you a positive or a negative sign at the end of your mathematical operation. So looking at the Gibbs free energy equation, delta G equals delta H minus T, which is temperature, times delta S. Since your enthalpy and your entropy, they can be positive or negative, right? You can have a number positive or negative for enthalpy depending on your process, if it's endo or exothermic. You can have a positive or a negative sign for delta S depending on your process is becoming more organized or less organized. So I have a summary of all of the signs and what we can expect to get for the delta G. So the first column on the table represents the signs for the delta H. And then we have a column for the delta S and then what we are expecting for the delta G. When you have a negative sign for delta H, that represents an exothermic process, right? And then for delta S, the positive sign represents spontaneous because when things are becoming more disorganized, that's something that happens spontaneously. That's the second law of thermodynamics. So positive sign for delta S, negative sign for delta H. Your delta G will always be negative. Now let's think about this. When you have a negative sign for delta H, that represents an exothermic process. It means that amount of energy it's being released from that process. That's that negative sign. Now when you have a delta S with a positive sign, it means that that process, whatever is happening, is becoming more disorganized. So amount of energy it's been released because it's not being used to organize things. So you have an amount of energy from your enthalpy because that process is exothermic and it's releasing energy, and then you have an amount of energy due to the randomness. It's becoming less organized, so you have energy there. So it makes sense to have a negative sign for the delta G because everything that is happening is actually releasing energy. So it makes sense for you to have a net amount of energy at the end. So that's why when you have a negative sign for the delta H and a positive sign for the delta S, you will always get a spontaneous delta G with a negative sign. Now, the second row in that table at the end represents the opposite. You have a positive delta G, non-spontaneous process. Now, that's going to happen because if you have a positive delta H, right? Positive delta H represents an endothermic process. When you have an endothermic process, for that process to actually happen, it requires energy. It has to absorb energy in order for that process to actually happen. For the delta S, you have a negative sign in that second row. So positive delta H endothermic requires energy. Negative delta S means that whatever is happening is becoming more organized. So more organized means that energy is actually required to have things organized. So you need energy for the process to happen. You need energy to organize things. There's no way that we can get a net amount of energy that is not being used. Whatever amount of energy can be produced in that chemical reaction, for example, it has to be used because your process will be absorbing energy and because your process is becoming more organized. So we don't have a spontaneous uh, process happening. Your delta G will be positive because energy is required for everything. Now the last two, we can get a spontaneous process happening when you have an endothermic reaction and your delta S is positive. I'm looking at the third row in the table, positive and positive. When the sign of your thermodynamic functions, enthalpy and entropy, are equal to each other, so I have two positives right there, you're going to have a negative delta G only if the temperature is high enough. Okay? So for the last two, the temperature is actually going to determine if you have a spontaneous process or not. And the easier way to look at this is with actual numbers. So we're going over some examples so you can see what this high temperature, low temperature represents. So I have a problem here, and I'm going to start the problem by writing the equation. So we're calculating the value of the delta G. So you have a numerical value for the enthalpy, a numerical value for the entropy, and a temperature. So to calculate delta G, we just need to plug in the numbers in the equation and we can get the answer. Okay? So pause the video, plug in the numbers, and get the value for your delta G. In this example, we have the same unit, so we don't have to worry about that. You have kilojoules for the delta H, you have kilojoules for the delta S. But whenever you're solving a problem like this, make sure that the given amounts that they have the same units, right? The equation is a subtraction, so if you have kilojoules and joules, you cannot subtract those numbers because they have different units. So try to solve the problem and come up with your final answer. So I'm going to start writing down my numbers. Delta G equals 3000 kilojoules, and that's minus my temperature is 298 kelvins times the delta S, which is 10 kilojoules per Kelvin. So this unit of Kelvin is canceling out because the delta S is given in units of energy per temperature. So you have kilojoules over kelvins. The unit Kelvin will cancel out. And then you have a number that is in kilojoules. And that number will be 2980. So we have a final number, and that number is a positive number, 3000 minus 2980 kilojoules. That will give you 20 kilojoules. That's the difference. So now let's think about the signs and what you were expecting for this delta G. You have a positive sign for the delta H. You have a positive sign for the delta S. So based on the table, when you have a positive sign for delta H, a positive sign for delta S, since you have the same sign for both of them, the final sign for your delta G is going to be determined by the temperature. If you check your notes, when you have positive and positive, delta G will be a negative number only at high temperatures. So these high or low temperatures are relative. Your temperature given, the temperature given here in this problem, 298, is not high enough for you to get a negative number for that delta G. You see, we're getting a positive value, so that temperature is not high enough. You can get a negative value for delta G, like a spontaneous process, when you have a positive delta H and a positive delta S, if the temperature is high enough. But that given temperature was not high enough. So I'm going to write down another temperature, and you're going to solve your problem and get your delta G with that new temperature. So use exactly the same values for the delta H, the same values for the delta S, but now calculate delta G when the temperature is 398 kelvins. Okay? So using the same values for delta H, delta S, but now at 398. Let's see if that 398 is high enough for you to get a negative delta G, or if that temperature is high enough for that process with those values for delta H and delta S to become spontaneous. So one more problem here. Now in this problem we're actually trying to determine at what temperature a process is spontaneous or non-spontaneous. For this example here specifically, we're trying to find out at what temperature a process will become non-spontaneous, which means that we're going to get like a positive delta G. Since we're trying to find temperature here, and this is my equation, so we're solving for T. You're given a value for delta H, you're given a value for delta S. Look at the signs for delta H and delta S. Both of them are negative, so you have the same sign for both. This is the last row on your table, negative delta H, negative delta S, and you will get a spontaneous process only at low temperatures. So if your temperature is low enough, when you do your calculation, you should get a negative sign. But high temperatures will give you a positive delta G or non-spontaneous. So we're actually trying to find out a specific temperature at which this process will become non-spontaneous. Whenever you have to solve for temperature using your equation for delta G, you're going to set up your delta G at 0, right? You have positive values, negative values. So you're trying to find out at what temperature, right, which value of temperature will start giving you positive numbers for delta G. So we're setting up delta G as 0. And then we can look at that temperature to find numbers that will give us negative numbers for delta G or positive numbers for delta G. So to solve this problem, you're solving for T, setting up delta G as 0, and you have your values for delta H and delta S. So try to plug in everything in the equation and solve for T, and pause the video so you can solve it and then come back and check my calculations. It should have units of kilojoules. Okay, I forgot. So it's delta G and we're using units of kilojoules. Your delta H, that's units of kilojoules. But if you check your numerical value here, for the delta S, that's a number in joules. So to plug in the number in your equation, both numbers, they need to have the same unit. So you can convert your 11 kilojoules to joules or your 17.4 joules to kilojoules. To convert joules to kilojoules, you have to divide by 1,000. So that's just the conversion from joules to kilojoules, so you can plug in the number in the equation. So it's the number 17.4 divided by 1,000. So you get 0.0174. And now you have kilojoules for both of them. Joules, kilojoules. So you have your enthalpy in kilojoules, your Gibbs free energy in kilojoules, your entropy in kilojoules. Everything the same units. So remember, we're trying to solve for T. Right here. So I'm going to start by moving my 11 kilojoules to the other side. So I have my 0 and then the negative 11 kilojoules on the right side of my equation. To get rid of that one, you have to add 11 kilojoules. So all of this plus 11 kilojoules, and you have to do the same thing on the other side. So 11 kilojoules will be 0 on the right side, and then on the left side you have your 0 plus your 11 kilojoules, which is going to be equal to you see how you have a negative and a negative, so you have minus T times negative, so those negative signs are actually canceling out. So you have 0.0174 kilojoules Kelvin times T. And on this side you have 11 kilojoules, 0 plus 11. So now I'm trying to isolate T, so I'm going to divide, since it's been multiplied by, I'm going to divide by so everything cancels there, unit canceling here. Here I have T, and this is 600, I'm rounding, 632. Unit that is not canceling out is Kelvin. So what that number represents, let's go back to the problem. This is asking you to find a temperature at which this reaction will become non-spontaneous. And non-spontaneous, what that means is that your delta G is a positive number. Remember, it's a negative number for spontaneous because you get a net amount of energy out of it. Positive number for non-spontaneous. So you're calculating a number that is 632, which means that at 632 you get a delta G that is 0, not positive, not negative, right? We set up that delta G as 0 in the beginning for us to be able to solve for that temperature using the equation. So at that temperature we get a delta G of 0, but any number above 632 will give you a non-spontaneous process or a delta G with a positive sign. Any number below 632 will give you a negative sign for delta G or a spontaneous process. So now I'm going to write down two temperatures, and you're going to use those two temperatures to find delta G using the same values that you have for delta H and delta S. So using the previous reaction, the same delta H negative 11 kilojoules, the same delta S, your negative 17.4 kilojoules per Kelvin. Now use those numbers to calculate delta G. At two different temperatures. And delta G when delta H is negative 11 kilojoules, delta S is negative 17.4 kilojoules per Kelvin at a temperature equals to 650 kelvins. So calculate your numbers and compare the sign. Which one of them is going to give you a spontaneous reaction? That's what you're doing for this one.